just.
Yeah, we can get started.
Okay. Morning, everyone. I'm Zhihe Zhao. I'm going to talk about my paper, Moses, exploiting cross-device transferable features for on-device tensor program optimization. So this is a joint work with my collaborators, including my advisor, Professor Guo Liangxing. So to begin the story, nowadays, deep learning models are getting bigger and more powerful. At the same time, the end devices we have, including mobile devices and edge devices, are also getting more and more heterogeneous. So a key challenge here is that how can we efficiently deploy the deep learning models on this diverse platform? So let me firstly walk you through the end-to-end process from the model generation to the model deployment on the end devices. So firstly, the developers will build their own models based on some machine learning frameworks such as PyTorch and TensorFlow. And finally, these models will be deployed on the different hardware platforms such as ARM CPU or NVIDIA GPU. So a lot of DN compilers have been proposed to bridge the gap between the high-level programming language-based models to the models running on the hardware codes. So some representative ones, including TVM and TensorFlow XLA. So here I give a real example of the state-of-the-art DN compiler named the TVM. So in this example, the TVM just transforms a PyTorch model into a series of multi-level intermediate representations, and finally generate the hardware backend codes in a very efficient manner. However, let us try to understand the bottlenecks of the DN compiler. So here I just give a matrix multiplication example. So the matrix multiplication operator is translated into the for-loop level tensor program by the DN compiler. So the key step here is to search the optimal tensor program configuration for this operation. And there will be quite a large number of parameters to be determined, corresponding to different optimization knobs, including, for example, blocking factor. So blocking factor is the way how people can determine the decomposition of the computations. So as I just mentioned, the parameters are has a very large number, and so is the search space. So you can imagine how time-consuming it will be for the DN compiler, especially on some resource-limited IoT devices. So the search process here is naturally interactive. So given a for-loop tensor program, we really need to measure the hardware performance corresponding to this for each tensor program configuration. And during the whole compiling process, there will be like billions of these kind of iterations. So however, there's a clever idea to introduce is the cost model. So the cost model here is to to predict the hardware performance for each tensor program configuration. However, the cost model itself is still hardware tightly coupled with the hardware. So the cost model cannot be directly transferred among all the hardware platforms. So to tackle this problem, our Moses adopts the idea of transfer learning of cost models among different platforms. So as you can see in this graph, cost model trained on device A is aimed to simulate the real hardware performance traces for each tensor program configurations. And if we do not want to train a brand new cost model on the new device, device B, then is it possible that we can adapt the cost model on device A and to device B? So the high-level idea of Moses here is to adapt the cost model to shrink the domain discrepancy. So let us zoom in and let me explain more details. So here is a key observation here is that the cost model contains two folds of information. The first part is hardware agnostic parameters, And another part is the hardware-related parameters. So the key idea of Moses is to distill the hardware-agnostic parameters which are useful for guiding our search. And inspired by the lottery ticket hypothesis, we proposed a lottery ticket-based knowledge adaptation method to during the online updating of our cost model to training it with pruning. And by doing this, our cost model can find the search space that contains the optimal tensor program configurations. And thus, the end-to-end compiling efficiency can be boosted. So let me walk you through the overall workflow of Moses. So the first step is that we pre-train a cost model on device A. And we directly transfer the cost model to the device B. And during the online updating or during the online compiling process, we adopt the training with pruning for our cost model. And here we also introduce a novel module named adaptive data sampler, which we further utilize the domain information. And we also developed a criteria for it. So to compare Moses with other works, if we train with fine-tuning like Tensor did, so the search efficiency may be good. However, the quality, or say the end-to-end latency for the tuned model may be bad because the cost model inside of it contains some noisy information, which just I mentioned, the hardware-dependent information. If we train from scratch, then the quality maybe can be promised. However, the search efficiency, like I just said, that it will be a quite time-consuming process for the compiling. So basically, Moses takes into consideration of both two metrics. So here is the evaluation part. So we pick up two representative baselines, answer and Tensor fine-tune from our experiments. So the first metric to analysis here is the tuned model speed up. And you can see that here's the benchmark is to transfer from the NVIDIA K80 to NVIDIA 2060. That Moses can outperform the two other baselines. And also for another benchmark is K80 to NVIDIA TX2, the similar things happen. And we can know that Moses can improve the auto-tuner search quality. So similarly, when comparing the tuning efficiency, then Moses can also outperform both of the other two baselines. So there are multiple potential directions for Moses to extend in the future. The first one introduced here is the auto-tuning search space pruning. So what we know is that there are quite a lot of edge devices that have some particular or special knowledge to utilize. For example, we all know that for NVIDIA TX2 that there is a shared memory space for both CPU and GPU to using. So this kind of information, maybe it will be useful or helpful for us to further partition the search space before the tuning process. So which will further boosted our tuning or compiling efficiency. And another potential direction is energy-aware DN compiling for edge devices. So as we all know that DN compilers are mostly focused on to optimize the end-to-end latency of the tuned model. However, in the real world, in the most IoT scenarios, the edge devices or mobile devices are expected to be to run in a quite energy efficient way. So, so maybe is it possible that we can reshape or redesign the search space or the cost model to let the DN compiler to guide the search and find or generate some tensor programs that can be quite energy efficient? So here I would like to sum up some thoughts on the big picture for a machine learning system for IoT. So in the past few years, there are quite a couple of works that are focusing on the optimization on the adjacent stacks showing here, including like the IoT scenarios to the computer vision, or to the machine learning frameworks and down to the hardware libraries. However, most of these works are just at the adjacent stack. And Moses, as an initial effort for optimizations on multiple stacks. So we believe that by leveraging the extreme high performance from the lower stack, for example, hardware library stack, and directly use them in the applications like IoT scenarios, that will be quite helpful. So thanks for listening. That's basically my talk. And you can check our paper, and this is the link to our lab. Thank you.
Okay, we have 5 minutes for questions. Do you have any? I was trying to look for you to see whether you have questions so we can give you priority this time. No pressure if you don't know, but.
Yeah. Hi, I'm Roger from CMU. I was wondering, could you go back one slide? Or maybe it was 2 slides.
This one?
It was the one where it had torts. Oh yeah. So I know, for example, going from PyTorch to TorchScript, there are some packages that you can use, like AutoGrad, for example, that the TorchScript compiler doesn't support. And it seemed like most of your talk was focused on stuff like, lower level operations like, matrix multiplication.
Yeah.
Do you have plans to support, higher level PyTorch packages or packages for stuff like auto differentiation and other?
The matrix multiplication, and you mean the libraries such as auto gradation?
Yeah.
Is that kind of operator? Because I'm not quite familiar with that. Can it just be represented as an operator or something? Or are you asking whether this kind of compiler can support to boost the efficiency for auto degradation or something?
Yeah. So if you're going from PyTorch to TorchScript and your PyTorch code uses this auto differentiation function, you have to just manually compute those derivatives by hand because the compiler won't do that for you. And so I don't know if your project, if you have thoughts on supporting those sorts of features that like PyTorch currently doesn't.
Because I'm not quite familiar with the auto differentiation, so I'm not sure.
Okay.
Okay.
All right, so I guess a quick question. Are you familiar with the neural architecture search?
Yep. A bit.
Right. So what's your thoughts on? So there are some recent work on trying to search for the energy efficiency or a performance efficiency model for end devices. How would you compare your effort to those lines of work?
Okay, that's a quite good question. I think for NAS, for searching for some energy efficient models and compare it to compiling assisted one. Because compiling assisted techniques can be seen as no loss. It will have no loss on the accuracy of the model. However, the NAS is basically focused on the architecture of the model, the connecting relationships of each operator, and maybe will bring some accuracy loss. So I think these two techniques can be cooperate with each other. Yes.